Now start on problem. First we discuss about infinite set and axiom of choice. First we start from theorem. Let A be a set. Let A be a set. And then the following statement about A are equivalent. Then the following statement about A are equivalent. First, there exists an injective function z plus 2a. There exists an injective function if z plus 2a. Number 2, there exists a bijection of A with a proper subset of itself. Number 3, A is infinite. Now we first 1 implies 2. We assume there is an injective function f z plus 2a. There is an injective function. There exists an injective function f z plus 2a. Let the image set f z plus be denoted by b. Let fn denoted by an. Because f is injective, a not is equal to am if a not is equal to m. Okay. Define G A to A difference A1 by the equation and Gx equal to x. Then the map G is indicated symmetrically, and one checks easily that it is a bijection. So it is a bijection. Okay. Now we prove there exists an injection if z plus 2a, then we get a bijection also G an to an plus and gx to x if a not equal to a difference b. Okay. Then it is a bijection, and next we show that 2 implies 3. We easily proceed this one. There exists a bijection of A with a proper subset of itself, then A is infinite. We know that A is finite, implies that there exists a bijection with a proper subset of itself. There does not exist a bijection, there does not exist a bijection. Okay. Then this implies that contra positively contrapositive is there exists a bijection of A with a proper subset of itself. This implies that A be finite. Okay. Next, 3 implies 1. That means A is infinite implies there exists an injective functions f z plus 2a. Okay, we start about now 3 implies A. That means A is infinite implies that there exists an injective functions f z plus 2a. How we proceed this one? A be infinite. Okay. Then construct an injective function, construct an injective function f z plus 2a. Okay. How we construct it? Since the set A is not empty, First, since the set A is not empty, since A not empty, then we choose A1 of A equal to F1, and assuming we have F1 F2 dot 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 Fn minus 1. Okay, we wish to define Fn now. The set A difference f of 1 2 dot 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 n minus 1 is not empty. For if it were empty, the map, this would be a surjection. The map to A would be a surjection, and A would be finite. Hence, we can choose an element of the set. And define Fn to be this element. Using the induction principle, we have defined F for all n belongs to Z. Now it is easy to show that F is injective. Now we show that F be injective. For m less than n, the Fm belongs to the set F of 1 2 dot 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 n minus 1, whereas Fn does not. So therefore Fn not is equal to Fm. Okay. Next, we discuss the existence of a choice of functions and axiom of choice. Given a collection A of disjoint non-empty sets, there exists a set consisting exactly one element from each element of A. Given a collection A of disjoint non-empty set, there exists a set C. There exists a set C consisting of exactly one element from each element of A. That is a set C such that C is contained in the union of the elements of A. C is contained in the union of elements of A. And for each A belongs to A, the set C intersection A contains a single element. Given a collection A of disjoint non-empty sets, there exists a set C consisting exactly one element from each element of A. A set C such that C is contained in the union of elements of A, and for each A belongs to A, the set C intersection A contains a single element. Now, existence of a choice function. Given a collection beta of non-empty sets, not necessarily disjoint, there exists a function CB to union of such that CB is an element of B for each B belongs to script B. Okay, given a collection beta of non-empty sets, there exists a function C B to union of B belongs to script B such that CB is an element of B and for each B belongs to script B. Then the function C is called a choice function for the collection script beta. Function C is called a choice function for the collection script beta. Now proof of lemma. Okay, given an element B of script B, we define a set B dash as follows. B dash equal to Bx such that x belongs to B. That is, B dash is the collection of all order pairs. B dash is the collection of all order pairs whose first coordinate is B. Okay, then second coordinate is an element of B. Second coordinate is an element of B. The set B dash is a subset of the Cartesian product the set B dash is a subset of the Cartesian product script B because B contains at least one element X. At least one element X. and the set B dash contains at least the element and the set B dash contains at least one element, so it is not empty. Now we claim that if beta 1 and beta 2 are two different sets in script beta, then the corresponding sets are disjoint. For the typical element of B dash is a pair of the form for the typical element of B dash is a pair of the form from B1 x1 and the typical element of B dash and the typical element of B2 dash here B1 dash is a pair of the form B2 x2. No two such elements can be equal. No two such elements can be equal, for their first coordinate are different. Now let us form the collection. Now let us form the collection. Let us form the collection C script C beta dash such that beta belongs to script beta. It is a collection of disjoint non-empty subsets. It is a collection of disjoint non-empty subset of script B union B belong to script B. By the choice axiom, there exists a set C consisting one element from each element of C. By the choice axiom, there exists a set C consisting of exactly one element. Consisting of exactly one element from each element of C. From each element of C. Our claim is that C is the rule of desired choice function. Our claim is that C is the rule for desired choice function. In the first place, in the first place, C is a subset of in the second place, C contains exactly one element from each set B dash. Therefore, for each B belongs to B dash, the set C contains exactly one order pair. Bx, whose first coordinate is B, whose first coordinate B, thus C is indeed a rule of functions from the class. Thus C is a rule of function from script B to union of B belong to script B. Finally, if Finally, if Bx belongs to C, then X belongs to B, so that CB belongs to B as desired. So today stop here.